All right. I think we can get started. So hi and welcome everyone. My name is Martin Schütz. I'm the global lead for the Amazon Advanced Solutions Lab. First, I want to thank the organizers for having me. And today I want to share with you our journey together with our partners and customers in our search for applications of quantum computing in industry. But before I get there, I wanted to share a little bit of personal background for at least two reasons. Originally from Germany, but my academic journey brought me actually to a place very close by here in New England, working at Harvard University with Misha Lukin. And the second reason, then a few years ago, I decided to try my luck as a scientist in industry and help build, as a scientist, the Amazon Quantum Solutions Lab, and then now today lead the Amazon Advanced Solutions Lab. If you're interested and curious about, in particular, this transition from academia to industry, then feel free to come to me, and happy to talk after this presentation. Okay, so now I want to kick us off with some example work that we do at the Advanced Solutions Lab. By no means complete, but really as a seed for inspiration and questions. And I want to kick us off here with a video taken on site in the paint shop at BMW in Munich, where you see several robots that perform a task that is called PVC sealing. So whenever you have an incoming car body and you have two or more metal sheets that meet, you have a seam. You actually have hundreds of these seams that need to be sealed with PVC. That's important to protect the car against corrosion, for water tightness, for soundproofing, etc., etc. And so BMW asked us to find the optimal solution to this problem. You want to do this as fast as possible, and that's actually a complex problem because you have to assign hundreds of seams to these robots, and then you have to determine the optimal sequence of these seams for every robot, much like the famous traveling salesman problem, but it's a highly decorated, complex version thereof, because you have to optimize over many degrees of freedom, not just quote-unquote the optimal sequence, but you also have to find the optimal angle, the optimal tool, the optimal lateral movement. So all of these degrees of freedom you have to optimize over as you try to find the best solution for this problem. And I think this is a very representative example for the work that we do, for at least three reasons. First, it's centered on a real-world, complex, large-scale industry problem called robot path optimization. Second, BMW, with a mandate from their CEO to better understand the potential implications of quantum computing for their business, asked us if this is a problem that could be sped up in the future, potentially with a quantum computer. And so we developed a deep, thorough assessment with a proof of concept on real quantum hardware. Disclaimer, it's not competitive with state-of-the-art classical solutions today. But we did not stop here. We actually also developed a state-of-the-art classical solution that is deployed today in production and is 10% faster than what BMW used before, with a new algorithm framework that we invented. It's called RKO. I'm not going to go into the details. Random Key Optimizer, a very flexible approach that can also be applied to similar problems like vehicle routing, bin piping, many other optimization problems that companies like BMW have today in the real world. Okay, the second example I want to talk about goes back to a science paper in 2022 from a team from Harvard, MIT, and QAero. And they reported on a very interesting result, a potential quantum speedup for an optimization problem, an NP-hard optimization problem, with arrays of up to 289 qubits, so pretty large quantum systems. and not just for some contrived mathematical problem, but actually for the maximum independent set problem. And they did this through experimentally benchmarking the quantum algorithm's performance against classical simulated annealing, observing a superlinear quantum speedup, and finding the exact optimal solution to this problem. So the main result is a little bit convoluted. It's shown in this graph, but in a nutshell, it's showing the success probability to find the optimal solution for a given instance. Red is the quantum algorithm, blue is the classical algorithm. The higher the better, and the reported quantum speedup is based on the fact that the red curve is higher than the blue curve, better than the blue curve, and shows a benign, a better scaling as you scale to harder and harder instances to the right. So this is a very interesting problem. And we started working with JP Morgan Chase, one of the largest banks in the world. And we deeply thought about this problem and potential ways that this problem could actually find applications in finance. And what we came up with is that if you take historical data, expected returns, correlation matrices from thousands and thousands of assets, you can actually build what is called an asset graph, where every node represents an asset, and correlation between assets are represented by edges. And then finding the maximum independent set problem is actually a risk diversification strategy. You see here a small sample graph in the framework that we built on the application layer. You're given a graph and you're asked to select as many nodes as possible, but you cannot select nodes that are adjacent or connected because these would be correlated. But you want to find a diversified portfolio here, and that's exactly canonical maximum independent set problem that now finds applications here within an extended portfolio optimization pipeline. We can solve this with an algorithm that we developed. It's called Q-Redomis. I'm not going to go into the details, but it's a hybrid algorithm. So you have a quantum computer that works in tandem with the classical computer, back and forth, trying sort of to use the best of two worlds. You use the quantum computer as an inherent sampler that provides candidates to be in the set, so assets that you should select for your optimized portfolio. And we showed that this can run on a hardware layer that could either be Rydberg atom arrays. So this is what was used originally in the Harvard work. That is something that we then used on AWS in the cloud to benchmark this with real data on benchmark instances. But you could also use the paradigmatic quantum circuit paradigm to power this larger framework. So the top result is then, on the left, you have the original results from the science paper 2022. First, on the right are our results. We went to larger, harder instances to the right. And yes, we verified in red that even if you take an optimized quantum adiabatic algorithm, ultimately, if you go to very hard instances, your success rate is going to plummet. It's going to go down and it's going to be 0. But what you can do is, and that's what we did, is if you invoke these classical reduction kernelization techniques that allow the quantum computer to really focus, zero in on what is the hard kernel of the problem, you can actually stay all the way up there for a very, very long time at the optimal success rate of 100%. The third example I want to share with you, and that's again here local, New England. It's work that we did with Fidelity Investments. So in many situations when the stakes are high, in healthcare or in finance, even the most powerful deep learning black box models are not good enough, because you need explainable models that you as a human can understand and interpret. If you accept or deny alone applications, you better have to justify your reasoning. And that is something that you can do with explainable AI. And we developed an optimized framework. An example is shown here, from this loan application example. It shows a simple Boolean formula, and we developed a framework that finds the most expressive Boolean formulas and showed that this works better than standard approaches such as decision trees, and even pinpointed a potential plug-in for quantum hardware because certain subroutines in this optimization problems in the future could actually be speed up through a quantum algorithm because these subrams are native to what a quantum computer is good at. Okay. So these were three sort of sample problems that we have worked on across automotive and finance. Hopefully, it became clear that there's a lot of value to unlock somewhere at this intersection between quantum, machine learning, HPC, and optimization. One thing I want to emphasize is no matter what technology you use, always this is preceded by developing an efficient mathematical model. You can develop an efficient model, you can develop an inefficient model. If you have an inefficient mathematical model, you're at disadvantage already from the get-go, no matter what technology you use at the end of the day. But if you look at these technologies, arguably quantum computing is, to some extent, maybe the most bizarre for all of us. So just talking about the elephant in the room here, what is a quantum computer? In a nutshell, quantum computers are machines that use quantum mechanics to perform calculations in novel and improved ways. Or in other words, it's not just a classical computer that runs faster, but really a new paradigm, arguably the next compute frontier, that leverages the somewhat intricate and bizarre laws of quantum physics to perform calculations in novel and improved ways. These quantum mechanical predictions, they look bizarre to us because we live in a macroscopic world, but if you consider the microscopic world, single electrons, single photons, single atoms, these quantum mechanical predictions, they have been tested over the last few decades up to the point that we now want to exploit these fundamental laws to make completely new machines that use superposition and entanglement principles that we have only in the microscopic world to solve problems that may otherwise be intractable. So where do we anticipate potential applications for these quantum computers? I've sort of broken this down here into four main categories: physics, chemistry, and material science on the left. This is somewhat intuitive to understand because in these domains you find problems that are inherently quantum mechanical. Take, for example, drug development. Ultimately, you have to find the optimal electronic configuration of a large molecule, so you have to solve Schrödinger's equation. That's inherently a quantum mechanical problem. There's arguably no better machine to do that than a quantum computer per se. Similarly, take our quest to build superconductors. For that, you have to understand the behavior of many strongly correlated electrons. Again, you have to solve Schrödinger's equation. Arguably, no machine better to do that than a quantum computer. But what's maybe even a little bit more striking is that in the 90s, then Peter Shor showed that these machines could actually find applications even in the classical world. And Peter Shor then with the Shor algorithm showed that it could find in particular applications in cryptography, showing that factoring large numbers, which is essentially the backbone of RSA, because this problem is mathematically hard to classical computers. There's no efficient classical algorithm for that problem. And as Peter Shor showed, this is actually a simple task for a quantum computer, giving you an exponential speed up over the classical best algorithms. And then so this kind of kick-started the field of quantum computing, quantum information, and over time we expanded our aperture. We looked left and right, and we even found potential applications in optimization and machine learning in examples like portfolio optimization, like I showed you with our work with JP Morgan Chase, resource allocation and machine learning, in speeding up some of these subroutines, matrix multiplication and what have you, that are standard in machine learning. Okay, and so because of these undeniable, fantastic outlooks of potential applications of quantum computers, about 7 years ago, we launched a larger effort at AWS, Amazon Web Services, around quantum computing that essentially consists of 3 pillars. From left to right, we have Amazon Braket. That's our cloud service for quantum computing. So already today you can log into the AWS cloud and get access to several quantum computers. The idea being that, we give you a one-stop shop experience to different technologies, from trapped ions to superconducting qubits to neutral atoms. The second one is the Center for Quantum Computing. This is, you can think of like our own R&D, in-house R&D effort. It's located on the campus of Caltech, where we build our own quantum hardware. And then last but not least, the Amazon Advanced Solutions Lab. That's the team that I lead and our customer-facing team. We work directly with our partners and customers in better understanding advanced technologies, in particular quantum computing, and help them build a strategic roadmap around these emerging technologies. So just want to briefly step through this. On Amazon Braket, already today publicly available, you can have access to 7 different quantum devices that include different technologies, from trapped ions to superconducting qubits all the way to neutral atoms, with tens to hundreds of qubits, and all of them provided to you sort of within one unified user experience. Next, the Center for Quantum Computing. This is where we build our own quantum computing hardware. We had a Nature paper last year that shows you all the glory details in this particular approach that we take. It's based on a hardware-efficient quantum error correction scheme based on bosonic qubits, also called cat qubits. I will not go into the details here, but in principle, you have the scientific reference in this Nature paper. One analogy that I want to entertain a little bit between GPUs that are, the powerhouse that power most of our, or if not all of our AI technologies today, is that these, if you look back, they started out in a niche market for graphics rendering, and ultimately on a journey through scientific computing applications found broad adoption through the ChatGPT moment, through generative AI and everything that has happened over the last few years. And time will tell if this analogy is right, but you can at least make a connection here that QPUs today are a niche market as the ultimate system for rendering physics models, and could, I believe, find broad applications in chemistry, materials, AI optimization, some of these target domains that I mentioned, through first applications in scientific computing. Very much akin to the journey that we've seen in GPUs and AI. Okay, and then I want to talk about a little bit more about the Advanced Solutions Lab. Our mission is, so to speak, twofold. We want to prepare every customer for the quantum future, future-proof your business, better understand what this technology could entail for you and your business, but also strive to provide business value today. And this is where we open our aperture beyond quantum computing per se, looking at an interdisciplinary mix of technologies involving quantum technology in particular, but also optimization, and machine learning. And with that, we always sort of try to deliver against these sort of two different dimensions. And this is why we have over time grown expertise across these three different areas. Example use cases that we work on, I've shared just three with you. The robot motion problem, portfolio optimization, and I've given you an example in explainable AI. But other canonical examples are NP-hard optimization problems such as vehicle routing, flight scheduling, sports scheduling, workforce rostering, clinical trial enrollments, etc. So these are kind of example problems that we've, fascinating problems in the real world that we have worked on over the last few years. The framework that sits behind this, it's not cookie cutter framework, but it is actually something that is deeply rooted in the Amazon DNA. It's the working backwards principle. Applied to quantum computing, what this means is that we typically want to first really identify a good candidate target use case. Once we have established such a target use case, so it should fulfill certain criteria. It should be hard. It should be hard today. It should have potential inroads for quantum algorithm, quantum advantage in the future, etc., etc. So then we can build. Today we can build quantum computing prototypes. They're little to no off-the-shelf solutions, so really built here typically from scratch. But then if you really want to be transparent in the capabilities and the roadmap for quantum computing, you have to do a thorough exercise called benchmarking. And this is where we sort of fan out into state-of-the-art deep learning solutions or classical optimization solutions to really give a transparent benchmark for quantum computing algorithms. Once you have sort of this transparent bar, you can build what we believe a reliable, larger strategic framework around this technology for your business. And that's something that we typically do then with our customers. So I want to give you two more examples that sort of showcase how we have employed this framework in practice. One was with the Australian Red Cross Lifeblood. So what is the problem that they have? They collect over 1.6 million blood donations every year. They have to assign nurses to time slots such that the registered donors can be serviced. There are many constraints in this problem. You have to make sure that every slot you have to have at least a certain number of nurses with a certain skill set. But you want to do this in optimal fashion to minimize costs. And the solution that we came up with is actually shown in this figure. On the vertical, you have, I believe, 40 different nurses. And you show and you see their schedule over the time frame, or optimized schedule over the time frame over 2 weeks. This is calculated with a state-of-the-art classical solution that we built using constrained programming. If you set up this problem mathematically, you will have to deal roughly with 85,000 variables and more than 800,000 constraints. So it's a significant problem. But we were able to solve this to optimality using efficient constrained programming, and this has brought 7% reduction in staffing costs due to more efficient scheduling, and even more so has given the Australian Red Cross now the ability to run certain what-if scenario analysis, so you can sort of place through different analysis what happens if our demand goes up by 20%, etc., etc. The next example is another large-scale optimization problems where we actually worked in-house with our colleagues at Amazon Transportation Services. Whenever you go on Amazon, it's going to tell you if you buy this product in the next 2.5 hours, you're going to get it tomorrow on your doorstep, right? That's our next day delivery promise. And ultimately, the goal here was the question: how can we extend this next day delivery coverage? How can we make these 2.5 hours maybe 2 hours 40 minutes? And if you backpropagate this problem through our entire middle mile network, essentially it boils down to how much can we push out the departure times of the last trucks, leaving between our supply warehouses, our sorting centers, and our distribution centers. So how much longer can we wait till we shut the doors of the final truck? We've solved this problem for our entire network in Europe with thousands of nodes, and using our custom random key optimizer and constraint programming. Nothing quantum here, just to be clear. We found improvements over the existing efforts that ultimately translate to tens of millions of dollars by increasing next day coverage. Okay, so last but not least, I want to give you a little bit of a framework, because obviously there's a lot of talk about AI these days. All these efforts, how we can sort of bring them together with this larger AI framework, where generative AI, which powers ChatGPT and all these LLMs, is just part of a deep learning, which is just part of machine learning, which is just part of AI. And some of the techniques that I mentioned, in particular, they allow for exact reasoning. And that's important because that's also a part of artificial intelligence. And we use it, for example, through automatic reasoning to minimize some of our AI hallucinations that everyone has to deal with. So this is embedded in our Bedrock services, providing you mathematically correct guardrails. But also, this is where some of the mathematical optimization techniques that I mentioned come in, because they are state-of-the-art for dealing with hard constraints and long time horizons, something where we know that Gen AI per se is struggling with. So here it's important to distinguish between inductive AI. A lot of coverage is typically these days on inductive AI. This is if you feed a lot of training data, essentially the whole internet. Essentially what you try to do is, through looking at many specific examples, you try to infer broader conclusions, and you're going to get probabilistic best guesses. But on the flip side, there are state-of-the-art techniques that go under the name of deductive AI that do the opposite. So they take general principles, mathematically rigorous principles, and will give you, apply these to specific examples, and they can give you then definite yes, no answers, as opposed to these probabilistic best guesses. That's something that is important whenever the stakes are high. And so, in our larger journey towards new scientific discoveries, we try to, obviously we are very open and excited about agentic AI and everything that it offers, but I think we want to sort of complement these with complementary technologies. I discussed a little bit here two prime examples. One is techniques that allow for exact reasoning, everything that goes under the name of neurosymbolic AI. In particular, mathematical optimization that was used in some of the examples that I showed here today. But then also quantum computing, because ultimately this will be the technology, the best fit for microscopic problems that involve quantum mechanical laws of physics. And with that, I'm done. Happy to take questions, and thank you.